Welcome, everyone. So I'm with Bloomberg. Want to talk to you today about custom resource definitions and kind of an interesting finding that my team's had with managing lots of Kubernetes platforms, which is actually the need for a data architecture kind of discussion with CRDs. And so with that, we've got this challenge of managing Kubernetes clusters at scale. I think Joe's talk was a great entry into this when you have thousands of clusters. I think in Joe's case, how do you manage Kubernetes clusters at scale? And in particular, when you're doing your Kubernetes clusters with Kubernetes. So my organization at Bloomberg is a Kubernetes first software organization. We live CRDs, we live controllers. And in particular, we've started coming up with CRDs for our Kubernetes platforms, kind of what we actually host various projects and software platforms on, but then the tiers of those platforms. You could think of these maybe as organizations. If you are a hosting company, might be your customers would be platforms, and those tiers would be their deployment tiers. And then at the end, you have your various clusters. But ideally, we're all running Kubernetes to run an application. So at some point, you have to deploy a namespace and actually put things on your Kubernetes cluster. One of the interesting challenges, if you're managing Kubernetes with Kubernetes, is you'll have an API server to store all this data. Starts looking a little bit like a database, which is kind of an interesting challenge, perhaps. Similarly, of course, you'll want to use controllers to affect your broader world. Bloomberg, we're a very large organization, so we not only have our Kubernetes clusters, but all of the sources of truth in systems outside of our Kubernetes clusters that have to both reconcile in or we have to reconcile out to. And then, of course, controllers to affect those platform clusters. So with that, let's kind of dig into the CRDs. One thing you'll notice here, if there's text in yellow, that is an upstream open source component or component from Kubernetes, one of the special interest groups like SIG multi-cluster, for example, from Kubernetes. If it's in pink, it's specific to Bloomberg and what we've built. And just trying to motivate a conversation here, because it sounds like a lot of folks in this room perhaps have had these problems, but I don't see it too often discussed externally. So with that, we've got these platform tiers, clusters. We want to actually kind of aggregate clusters into cluster sets, and we've got this interesting concept called a compute namespace. So Kubernetes has a namespace, but quite often you have a lot more metadata than just a namespace specification. So let's talk about what we mean by platforms. In particular, Kubernetes platforms that we have at Bloomberg, and we have some cool stuff in my mind. We have Apache Spark running data analytics, usually in a batch workflow system. We've got Apache Flink running on Kubernetes, which a nice streaming processing infrastructure. We've got Argo for workflows, either to schedule jobs on these platforms or on other systems, as well as Jupyter Notebooks, because it's always nice to have humans actually using computers, and so Jupyter gives a very nice window to do that. And often, AI, of course, has to happen somewhere, so model development and training for AI and Kserve for inference, which runs again on Kubernetes clusters. So when we talk about scale, for us, that's about 9,000 software engineers, so definitely a couple folks that we have to make this pretty straightforward for and deploy their applications. So one of the questions comes up is, how do we decompose a platform, right? So we've got something like Kserve or Jupyter running on a Kubernetes platform, but how do we decompose that? And then how do we scale so that my team, which is responsible for all this metadata on how these platforms work, can actually scale out where we're not going crazy trying to figure out what's different between all of these platforms? So let's kind of just sit back and quickly take an SRE view or a DevOps view of the world and understand what a tier of one of these platforms might look like. Tiers are contained within a platform, and keep in mind each of these pink terms right now is a CRD. So we've got the platform CRD. We have a tier CRD. These tiers roll up to a platform CRD. For us, a tier is kind of the highest level to define a useful configuration. Usually a platform doesn't have a lot, right? It's really hard to abstract out and say, every Kubernetes cluster running Spark is going to have some axiom about it. But at a tier level, I can start to rationalize that there might be access policies, right? I probably don't want all my developers logging into a prod system, but dev might be a little okay. Similarly, resource usages. Each cluster is going to be different, or at least each tier is going to be different with what it supports. Again, let's think about AI. If you've got a bunch of GPUs, probably going to have to think about resource usage a little differently between prod and dev. Similarly for network controls, again, kind of tautologically, those are going to be different. But then when we start to actually roll up these tiers, we've got cluster sets within them. And for us, that's kind of an availability zone sharding system, or it can be a sharding system for how applications might be deployed to one of these tiers. So basically, one or more clusters will roll up into a cluster set. This kind of brings us to the concept that my team really wants to make sure all of these platform teams are thinking about is their clusters are cattle, not pets. This was a common term a decade ago, right? Think of your machines as cattle, not pets. You don't want to hand build a system. You want to have just infrastructure as code, and thankfully we've come to this world now where Kubernetes exists, but start thinking of your clusters much more as cattle and not pets. So we want to manage clusters in aggregate by tier, and this brings an interesting question. If we've got all these clusters rolling up into a tier, perhaps some of you have heard a concept called the namespace sameness principle, and we'll cover that later in this talk. But here, think about this as a cluster sameness principle. Clusters within a tier, the way our system's defined, have to be feature homogeneous. So that means that you don't have maybe a Spark and an Argo cluster in the same tier, because they would be in different platforms. You wouldn't have a cluster that maybe has GPUs in a tier and another cluster in that same tier that doesn't have GPUs, because you can't deploy an application homogeneously to any cluster within that tier. And to kind of give just a concrete example here, let's say we've got a platform like the Spark platform. Under that, we might have tiers such as runtime development, end user development, beta, and then maybe multiple tiers even, like at a certain level, like production here. So let's walk through Kubernetes namespaces. This is, after all, what my team is looking to deploy. We want to make sure that we've got containers ready to accept applications on each of these platforms. And so the platform teams deploy applications, again, that's out of scope for my team and this talk. But the namespaces, at least, will now be ready to accept those applications and have all the resource controls they need. So that compute namespace CRD we have is associated with a cluster set. Basically, that compute namespace has to actually know where it's being deployed. The cluster set is that deployment home. Compute namespaces define that Kubernetes namespace, and so quite often these are the axioms like service accounts, limit ranges, resource quotas, RBAC, that might be necessary to define for a namespace, as well as business logic. Again, any company always has its special business logic, but all of that rolls up into the CRD. Again, namespaces are deployed at the cluster level, and here we've got a nice diagram just to kind of give you that visualization of how this rolls up. You can see here we've got two cluster sets, cluster set X, cluster set Y. Each one has a compute namespace that deploys into that cluster set, and then within that cluster set we have two clusters, X1, X2, and Y1, Y2, and then the actual Kubernetes namespaces that are created. So I want to step back. That's what my team does. That's how we've done it. What I'd love to motivate a conversation in the community about is SIG multi-cluster. So you can usually find me hanging out on the Kubernetes Slack in #SIG multi-cluster. And SIG multi-cluster really thinks about a lot of these issues. And the question is, how do we kind of roll it up to this level? Right now, we'll talk about namespace sameness here, but that SIG is the one that's really ratified what namespace sameness means. Similarly, there's a number of KEPs that have come out of this SIG, such as Multi-Cluster Services API. We'll dock in kind of how that relates to the work that we've done at Bloomberg, cluster inventory as well, which relates. But we won't actually talk about another KEP that the SIG's done, and I want to bring up why, cluster ID and the cluster property CRD, which is really cool work. We didn't happen to adopt it. It's where you can actually figure out when you're running on a cluster what that cluster might be able to offer, or just various material about that cluster. Our systems always come from the outside of the cluster in, rather than running in the cluster and introspecting out. So with that, let's dig into kind of the cluster profile, KEP 4322 cluster inventory, and what it defines with SIG multi-cluster. So on the left-hand side here, we've got SIG multi-clusters definition. On the right-hand side, we've got a decomposition of what our cluster CRD kind of specifies. There are some similarities, however. Display name, what you actually call a cluster is kind of key, right? We're still humans and we need a handle on what we call something. The cluster manager, for us this is rather implicit. We have one cluster manager, so we don't have to define that. But SIG multi-cluster is trying to build a framework that we can all adopt. So the cluster manager and where that might live is a key part of the cluster inventory. Similarly, status, the Kubernetes version, I think it was mentioned earlier today that CRDs came out, I think in version 1.16, but if you are running a cluster, you need to know what Kubernetes version you have so you know what features it supports. Similarly, conditions on the cluster, your cluster health, whether it's actually joined to your cluster management system. And then this goes back to why cluster, how our system works with deployment. Cluster access is a really key part, right? We all are used to working with tokens. We might have OAuth or other mechanisms on our API servers. But are we pulling data into the clusters with such as Work API and other SIG multi-cluster specification? Or are we pushing with, say, maybe federated identity? Or are we pushing with just a pure token? So all of this is defined in KEP 4322. Our cluster definition is a little more simple. We need status, and it's in some ways a little more descriptive too. We're able to say, hey, what is the status of this cluster? And we can actually set up the state there. So we've got inactive or active, right? Very, very coarse, but we could have cordoned, deprecated, or decommissioning. And this gives ideas for people deploying application to those clusters, what's the stability of that cluster, as well as a status message for humans, because otherwise it's hard to communicate. Similarly, cluster access for us is maybe there's certificate needs, maybe there's proxy needs. Server URL, regardless of where you're at, you usually need some way to find the API server. And for us, we still do have authentication configuration. It just doesn't quite fit the models from 4322, but we are still doing a pull model for our work. So with that, let's look at KEP 1645 multi-cluster services API. And this defines a cluster set in this SIG multi-cluster universe. And basically, one of the key things to think about is namespace sameness applies. And that basically means that any namespace deployed within a cluster set has to be the same on any cluster within that cluster set. One of the interesting implications of that from the cluster inventory KEP is that means that a cluster really shouldn't belong to multiple cluster sets, because now you have the risk that the namespaces might collide. So kind of a one-to-one mapping here. One of the key things we can look at here then is that ties very nicely into how our system's implemented with cluster sets. Here we could see Apache Spark platform has dev interactive, dev batch tiers, and within each tier we have two different cluster sets, an A cluster set and a B cluster set. One of the key things that's worth pointing out, again, with SIG multi-cluster is it tries to be very opinionated on what it can be and very open to implementations. So it doesn't have any implementations, it's just specifications. And here you'll see the specific mechanism is out of scope for this proposal as far as how tracking membership and defining membership for a cluster set is. So now let's dig into namespace sameness. I've referenced it a couple times. And the SIG multi-cluster definition is very nice. It's very short, concise. But permissions and heuristics are consistent across clusters for a given namespace. Namespaces don't have to exist in every cluster. So again, this is kind of a key part for our tiers. A namespace deploys into a cluster set within a tier, but may not deploy into other cluster sets in that tier. And they do have to behave the same, though, if they are deployed. And this is why we end up with that challenge that a cluster probably ought not be in multiple cluster sets. So for us, this works out very well. The compute namespace that has all of this bundle of data about a namespace is at the tier level, and this allows for consistent Kubernetes namespaces. And again, kind of a diagram to give us a nice visual way to look at that. So now let's dig into cluster names. And again, we all are humans. We like to have some way to handle things. So the multi-cluster services API defines a cluster name as something kind of obvious, a unique identifier for a cluster, scoped to the cluster's registry, how you're actually managing your clusters. Again, it's very nice and hands-off, says we don't really want to define the registry, that's up to you, but we just want to make sure we have this concept we all agree on called a cluster name. And again, it's used for definition in the cluster set. Again, also, it's really hard to change a cluster name, so clusters is cattle, not pet. Don't try to change the darn thing, just blow it away, recreate it, so it's an immutable state in that cluster. So now let's talk about the data and storage. We've got all of these different terms, we've got kind of an ontology of how this can go together, but this is where it starts to get interesting, right? We're talking about data concepts for our cluster management. So let's talk about where this all lives, and in SIG multi-cluster, that is the hub cluster. For us, we call that the Managed Compute API server. It is an actual Kubernetes API server. And then let's talk about, since this is kind of looking like a database, we can use etcd, it is a great data store. We could also use something called Kine, which comes from the K3S project. And now, well, we've just talked about databases. Let's talk about referential integrity of our CRDs. Wait, what? So that's one of the things that I want to motivate here too, because I have not heard this come out at a Kubernetes conference before, but we kind of have to start thinking about it when you're layering CRDs one after the other, referencing another. So KEP 4322 cluster inventory basically needs to reside on a dedicated Kubernetes cluster, aka that hub cluster. And so let's look at what our hub cluster, the managed compute cluster, looks like. Here we can see that we've got some cluster-wide CRDs, the platforms and tiers, and then we can see an actual namespace for one of those tiers in the kind of beige box here. So we can see two platforms defined, the CRDs for platform 1 and platform 2, very descriptive, and then tiers for dev and beta. Now, each dev and beta have to point to platform 1 because they are tiers in that platform, and now we can actually look at the beta tiers namespace. And so here again, we have cluster sameness and we have namespace sameness that have to apply, so that actually lives in a namespace on our managed compute API server. This server has no nodes, it's just storing data for us. It allows us to operate with Kubernetes controllers, it allows us to treat this like any other Kubernetes cluster because it just doesn't do workloads. So here we see cluster A and cluster B are defined, they're all in cluster set X, and then we've got 3 compute namespaces. So now let's talk about the high availability aspect, because you really don't want to lose your control plane usually. And so we use something called Kine from K3S. It translates the etcd API. So it actually will allow us to now, instead of using etcd, use SQLite. Well, that doesn't really give us high availability, but it's kind of cool for local development. But Postgres. Bloomberg, we've got an amazing Postgres team. They say, hey, yeah, you want Postgres? We can make that highly available and replicate wherever you need. So we use that. It supports a number of other databases as well. Nats is a very cool thing. I actually hadn't realized until I was reading the README for Kine. But with that, there's some key features of Kine. It can be run standalone. It's very lightweight. Basically, it works for any Kubernetes API server. It doesn't have to be specific to the K3S project. A key part that they want to make sure that everyone's very well aware of, if you have etcd doing some cool, crazy thing for you, they are not a generic etcd drop-in replacement. They only translate some of the calls, but the ones that Kubernetes API servers need, such as create, update, and delete, the transaction calls. And we use that so that way now we have multiple API servers that all can point back to our data, ironically living in Postgres, and we can manage our clusters that way. So let's talk about that referential integrity. We've set up that we've got platforms, tiers, clusters, cluster sets, and compute namespaces, but they all reference one another. And so we now need to make sure that, for example, you don't deploy a tier to a platform that doesn't exist. We need to make sure that we've got a compute namespace that actually is defined in a cluster set. And we need to make sure that all works out well. So some challenges with that are enforcements and updating. So we use cell expressions to make sure things are well formed, but that doesn't give us referential integrity. Webhooks do though. So now we can actually have a webhook that says, hey, let me make sure that platform exists that you've specified. Let me make sure that tier exists. Let me make sure you don't delete a platform that still has data. And now we can also have controllers. So you'll notice here our compute namespace, as I mentioned, has some business logic, such as on-call groups or owning user IDs. And those live in other sources of truth, right? My phone number doesn't live in a Kubernetes cluster. Well, it might, but that's not a metadata in a CRD field. So that has to go and reconcile out if I change my phone number. Similarly, who owns that, right? People like to change teams, so we have to actually push that in to the CRD and make sure it's bidirectionally replicating. So we have controllers to implement all of that. So let's talk about resource creation now. It's great you've got all these CRDs, but if they just live on a Kubernetes cluster, it really doesn't buy you much. So this is where I think it'd be great to have a discussion of how do people do this. For us, we have a pretty simple API layer. It is a Kubernetes client that reads our management cluster on the right-hand side. Again, kind of that straightforward process with the compute namespace. But now we have a replicator that, again, is kind of a controller. It is able to talk to that API, which basically takes a compute namespace and renders me a Kubernetes namespace YAML. And now I can just create that on the cluster. Each cluster knows this well-known API and API translation service, and it's able to talk to its local API server to create necessary resources. Similarly, this gets kind of more interesting because we have sources of truth for permissions that out of scope here, but they can generate OPA bundles. And so now I've just got OPA bundles running around on kind of something like an S3 bucket or what have you, and that translation service can pull those bundles down now and start to parse those bundles so I can query it and say, hey, what cluster role bindings should I have in this cluster? What cluster roles, et cetera? And that replicator service, as long as I'm generating those YAML specs, can inject that into my cluster. So with that, I think I'm out of time, or nearly out of time. And so, yeah, with any questions, I just want to make sure that everyone here kind of hears a call to action. I think there's lots of folks in this room probably creating similar systems. Let's have conversations on them with that. I think.
Hi, thank you for your presentation. Sure. I have a general question since I've been actually diving into multi-clusters myself. And the one thing that I did notice when going through multiple solutions is that each and every single provider, company creates their own multi-cluster. Why did you decide to build your own rather than use one of the currently available? I believe there's like a pretty handful of choices available, both supporting pull and push models, and with roughly functionality matching what you just described.
Yeah, so we do use Karmata, for example, today. We have looked at a couple other solutions. Ours is also relatively old. It actually predates me joining this team, which is about 3 years now. So we're kind of trying to figure out, to your point, Karmata is a great example. I'm drawing a blank on some of the others right now, but they do follow a lot of the specifications here from SIG multi-cluster, and that's one of the reasons I wanted to highlight. I ran this by a SIG multi-cluster call to say, talking about a lot of your work that I've not been involved in, but I want to make sure people know about, and they said, thank you, yes. We find people don't always know that these definitions even exist. And so being able to make sure that folks are aware. Things like Karmata, though, and a number of the other projects do actually implement these features. For us, the biggest challenge is things like translation with the OPA bundles, stuff like that, where we haven't yet been able to find a good way to upstream them or a good home for those features. So.
Hi, thanks for the talk and the inspiration with the SIG multi-cluster group, actually. You kind of lost me, though, once. The data model and the connection between the cluster set and the cluster inventory, cluster profiles and cluster inventories. Could you explain that again, please?
Yeah, so cluster profile really defines metadata about a cluster. So this can be, for example, right now there's a discussion in the community on access for how you define access to a cluster. So this is very similar to our internal cluster CRD, basically saying, what's the name, where, how do I access this thing, and all of the properties about a cluster. So, cool.
We have time for a few more questions. Thank you.
So you mentioned that you're using Kind and Postgre because you have an amazing Postgre platform, but does that run on the same Kubernetes? So like, do you manage those clusters that run Postgre and Kubernetes and then you use it for the entire persistence layer? Because that can make...
No, that's a great question. So admittedly, management of Postgres is out of scope from this talk for sure, but they are not, there's no stack dependence in this case. It is worth pointing out too that like our management clusters are actually really lightweight, but they do run in a Kubernetes cluster. So yeah, it is actually kind of funny that shortly they will be self-managing and we'll have a Bootstrap Inception challenge to overcome. So.
Last one. Cool, thanks for a great talk. So you said you're running a full-blown Kubernetes cluster. Is there anything
you need from that, like in terms of workloads, or have you been looking at KCP as well, which is doing similar things?
Yeah, so actually in this case, it's not a full-blown Kubernetes cluster. It is just the API server, largely. No nodes, no actual workloads running on it. So like all the controllers that reconcile against that are, again, running in the Kubernetes cluster that's hosting the API server that is our management cluster. KCP, pardon my ignorance off the top of my head, I don't have any pros or cons for it right now. We're able to do this with a pretty lightweight Helm chart, admittedly. So.
Thank you. With that, we're on time. Thank you, Clay.